So as you've probably noticed, the two biggest applications so far that we've looked at of calculus in this class are speeds like velocity, acceleration, and position. That's like the first main application of calculus, and econ, revenue, cost, profit, all of those things. There's a lot of calculus applications in that as well. So for the last part of today, basically we're going to look at revenue and things like that. Okay, so if you can recall, back from chapter 4, I think it was, or 3, I can't remember, marginal revenue was basically the derivative of revenue. So now in this chapter, we're focused more on antiderivatives. So you could say then that the revenue is the antiderivative of marginal revenue. So if marginal revenue is the derivative of revenue, that makes revenue the antiderivative of marginal revenue. So suppose you're given a company's marginal revenue, thousands of dollars per thousands of units. So it's dollars per unit. That's a rate of change, of marginal revenue. How much money, aka revenue, so how much revenue should the company expect from a production of 3,000 egg beaters? So if I want to find that out, I basically want to find the revenue of 3 because it's measured in thousands. I want to find R of 3, basically, is what I'm trying to do. So we're basically told the way to do that, the application of that is we integrate marginal revenue. We integrate marginal revenue from 0 to 3. We find the area under that curve. This integral is basically the antiderivative of this. So we take the antiderivative, or the integral, of the marginal revenue, and to figure out a value of the function, the actual revenue from 3,000 egg beaters, you just go ahead and plug the 3 in there. So we're going to find a definite integral from 0 to 3 of this, and that would give us our marginal revenue. Well, since we just learned how to use the calculator, why don't we go ahead and use it now? Okay, so let me clear that out. So basically all I have to do, and by the way, for these purposes, we want to use net area, not total area. We want to use net. So we're just going to go ahead and do a regular integral. So I'm going to do math 9. There's my function right there. So it's 2 minus 2 divided by, and I'll go ahead and put that denominator in parentheses to let the calculator know it's dividing by the whole thing. So it's 2 minus 2 divided by x plus 1 squared, comma x, from 0 to 3. And I get 4.5. So keep in mind what's going on here, because we want to know what 4.5 means. So I'm going to get to that in 1 second. This right here is measured in dollars per unit. This is dollars per unit. That's this part right here. Let me write it a little better. Dollars per unit. That's the function itself. The dx, if you can recall, this is like base times height. Height is measured in dollars per unit. The dx is number of units. So we're doing dollars per unit times units. That cancels out. So this right here should be in units of dollars, or whatever. It's measured in dollars because the units canceled out. When I did all these base times heights, base times heights, base times heights, this right here is dollars per unit. This right here is units. Boom, they cancel out. So when I evaluate this integral, my answer is in terms of dollars. But not only that, it's in terms of thousands of dollars. So the revenue from selling 3,000 egg beaters would be equal to $4,500. And so that's our answer for for number 8. So whenever you're given a rate of change, a marginal revenue, and you want to go back and figure out, well, how much revenue is that? You basically integrate. You take the antiderivative of marginal revenue, evaluate that from 0 to 3, and bada bing, bada bang, you've got revenue. So now we've come full circle. We're at the point now where we can use derivatives to find things, or if we're given derivatives, we can use antiderivatives to find things. We can go back and forth now. So with that, we're going to do our last sort of application, inventory. which is also part of, you know, econ and all that good stuff. So let's say that we have a function that keeps track of how many items we have on hand in any given day at our particular store or warehouse or whatever. And for inventory, we'll go ahead and call it I of x. So that's going to be the number of items on hand or in hand on any given day. On day x. So x is referring to days. I of x is referring to the number of items on that given day. So on a given day x, how many items are in hand? And this is sort of the inventory function. Well, we could figure out on average how many items are in hand by using integrals. Because if you remember from, I think it was 5-3, the average value of a function is just you take the integral of a function from a to b. You find that area under the curve, and then you just divide that out by the base, by b minus a, and that gives you the average height. So if you remember that from 5-3, here's our average value of any function. We can go ahead and apply that to inventory, and we could say the average daily inventory would just be 1 divided by b minus a times the integral from a to b of I of x dx. And we can use that to find the average daily inventory. How many items on average do we have on any given day x? Can be found by integrating and then dividing out by the change in days. And then supposing we assign a cost, supposing you have a cost h, which would be the holding cost per item per day. So it's like, okay, it's going to cost you, like in example 9, it's going to cost you 3 cents a day to hold one of these cases. And you want to find out, okay, so how much are we paying on average per day? You take your average value of I, which is the average number of boxes or cases or items on any given day. So you take that value. This is how many items you have on average in stock on any given day, and you just multiply that by whatever the holding cost is, and that would tell you your average daily holding cost. So let's go ahead and apply those formulas now in number 9. Okay, so number 9 we have says, suppose a wholesaler receives a shipment of 1,200 cases of boxes of chocolates every 30 days. The chocolate is sold at a steady rate. Of course, we like to keep things steady for this level of calculus to take out some of the variables. So just imagine it's sold at a steady rate, and X days after the shipment arrives, the inventory of cases still on hand is this function, 1,200 minus 40x. So that's our inventory function. So like on day 15 of the month, you could plug 15 in there, and then you could figure out what that would be. So on day 15, you've got 600 cases. On day 10, you've got 800 cases. And it kind of just tells you how many cases you have on any given day within that 30 days, every 30 days. So first they want us to find the average daily inventory. Okay. Average value of a function is code for the integral divided by b minus a. And in this case, a would be 0 and b would be 30 to indicate sort of one period of this shipment thing, because it's every 30 days. So one cycle of these shipments are from 0 to 30. So to find the average value of the inventory, I would do 1 over 30 minus 0 times the integral from 0 to 30 of this function, 1,200 minus 40x dx. That right there is going to give me my average inventory. So I'm going to go ahead and use my calculator to evaluate that. So I'm going to do math 9, that function, so 1,200 minus 40x, comma x, comma 0, comma 30. So that's all the area under this curve, but I want to figure out, so that's like the total number of cases all together from the 30 days. So I want to divide that by the 30 to figure out on average how many are there per every 1 day. I get 600. So my average daily inventory is equal to 600 cases. So on any given day, on average, I have about 600 cases per day. Okay. Then it says, okay, find your average daily holding cost. So if you have roughly 600 cases on hand per day, how much are you paying per day? Well, it's 3 cents for every one case. I've got 600 cases. So my average holding cost would be 600 cases at 3 cents a piece, which is $18 per day. So that would be our average cost, our average daily holding cost. And these are just some of the applications of integrals. There are many others, as you will see as we proceed. But we have basically arrived at the most important theorem of this class, the most advanced concepts. So you should be very proud of yourself. And of course, if you have questions, please come see me in tutorial. And I hope you have a great day.